Hello everyone, welcome to another physical sciences lesson, and our topic is all about electrochemistry. And we're going to be doing something rather special today. We're focusing on the table of standard reduction potentials. So let's go and have a look and see how this all fits together. So my first question to you that follows on from our previous lesson is the zinc copper cell the only galvanic cell that we're going to be looking at? It's quite an interesting question, and in fact we're going to answer it by looking at a series of information that we can get put together, which we call the table of standard reduction potentials. Let's see how this all fits in. So you'll remember that in electric chemistry we've got the galvanic cell, which we've spent some time on. We focused on the fact that it has an anode and a cathode. The anode is where oxidation takes place, and the cathode is where reduction takes place, because we look for the red cat and we look for an ox. They are joined by a salt bridge, and we know that we can draw diagrams of these, or we can simply put them into cell notation, where we have a specific order of putting those components. So we can show the electrode, what's in the solution, the salt bridge, what's in the solution, and the following electrode. We're going to practice a bit of that as well a little later. But what our focus today is on the redox reactions, and in particular the standard reduction potentials. We're going to be talking about this mystery, which I've put down as She. Now, She is really the standard hydrogen electrode, and we'll have some reasons to share about exactly what that's about. So let's move on and jump straight into our discussion today, and by referring again to what we've done previously, where we took some zinc and we placed it into a solution of copper, a copper solution. I think this was copper sulfate. After a little while, we took out the zinc and we found there was copper at the bottom there, and there's copper deposited on that as well. So the equation that we got was copper went into copper sulfate, zinc went into copper sulfate, and that produced zinc sulfate, and copper was the deposit. We recognized we could break that reaction into two half reactions, where we'd say zinc loses 2 electrons, those are the electrons there, to form zinc ions. This is therefore called an oxidation reaction. This is an example of direct transfer, where they're in contact with each other, where the copper solution has copper ions to start with, and it gains those electrons to form the copper metal. This is reduction. Please remember as well that this substance that undergoes oxidation is called the reducing agent. So the zinc here is the reducing agent, and it has donated its electrons. The copper ions here, copper ions, are the oxidizing agent because they've taken electrons. So this balance between oxidation, reduction, reducing agent, oxidizing agent, something you must be very familiar with, both for direct transfer, but also for what's happening in the galvanic cell. So we recognize the same sort of thing is happening here. It's the same sort of reaction where zinc at the anode is undergoing oxidation. So the zinc electrode here is the reducing agent, where in the other half cell, the copper ions are the oxidizing agent. And we're recognizing that's the reaction for there. It's undergoing reduction. That's the cathode, that's the anode. And remember that because this is the reducing agent, it's donating electrons, so electrons are going to move through the external circuit from the zinc electrode through the voltmeter, and it's going to end up on the copper electrode. anything that's a source of electrons is going to be a negative terminal, and anything that's accepting electrons is going to be a positive terminal. So the zinc electrode is considered negative, and the copper electrode is considered positive. Flow, or the movement of electrons from the zinc through to the copper, as I've indicated. And that gives us a reading on the voltmeter. And in this case, I want you to notice that this is a positive reading, telling us that this reaction is a spontaneous reaction. It happens without any energy because this is a galvanic cell. It's one in which we're finding electrical potential is converted into, chemical potential is converted into electrical potential energy. And it's the difference between the ability of these half cells to react or have a reduction potential is the reason why, when we connect them together, we've got this reading on the voltmeter. So let's explore that in a little bit more detail. And when we asked the question earlier about is the copper zinc cell, the zinc copper cell, the only one? Well, no, it's not, because we recognize that chemists have a way of comparing reactivity, what they call a reactivity series. And one other example of this is if we take copper wire and we place it into a solution of silver nitrate, there's another direct transfer of electrons. So it's direct transfer of electrons. It's an example of a redox reaction. But this time, the copper is the one that is going from copper to copper ions, plus 2 electrons. And this solution, that white stuff that you're seeing there, is actually the evidence of another reaction taking place. And I'm just going to change the color of my pen so you can see. What's happening there is the silver ions in the solution are gaining electrons to form that white substance that we see there, which is actually silver. So that's the silver that's forming there. So we can recognize there are a whole lot of these displacement reactions taking place, and that means that we should be able to get a whole lot of different electrochemical cells, which we know in this case, an example are also called galvanic cells, because they're producing electricity for us. As I said, these are displacement reactions, and by doing a whole lot of displacement reactions, we can get a series from the more reactive. These ones are more reactive, and these are less reactive. And you can do this by a number of ways. In the end, having a series like this, I want you to notice these are metals, group 1 metals here, and these are the transition metals. These are relatively unreactive, and in the middle is hydrogen. Now, here's our table of standard reduction potentials. Where it comes from, I'm going to explain a little later, but what I want you to see is it gives us an order of things in their ability to be reducing agents. So on this table, we see these are the strong reducing agents. And on the next slide, we'd recognize that this down here, fluorine, is the strongest oxidizing agent. Okay, and so as a consequence, let's just look at what the information this table is doing. We're going to zoom in on that reaction there, and we recognize the reaction with zinc. I want you to see that zinc going to zinc ions is the oxidation reaction. Whereas, if we could take the reverse reaction, in that case, this is the reduction reaction. So zinc can undergo both oxidation and reaction and reduction, but it actually prefers undergoing, if you start with zinc as a metal, it prefers undergoing oxidation. So zinc is a reducing agent. Now, in comparison to others, it's a fairly good reducing agent. But how do we know? How can we test it? Well, of course, the thing that chemists do is they do investigations and they compare reactions. And so I want to take you through the idea of comparing a zinc half cell to other half cells. But I think it's time for a short break. When we be back, we're going to investigate She in more detail. So see you after the break. Welcome back from your break. We're going to be comparing some half cells. Those half cells put together make a galvanic cell. So remember, this is our focus, and we're going to look at She, the standard hydrogen electrode. Before we get into that, let's just talk about the idea of a standard. What do we mean is a standard? Well, in chemistry, you have a whole lot of standards depending on what substances we're looking, what calculations we're doing. So, for example, the standard for a mole, 1 mole is related to 12 grams of carbon isotope 12. And so everything is compared to that. We could also look at the standard volume for gases, and we'd say the standard volume is 22,4 decimeters cubed at a temperature of 273 Kelvin and a pressure of 1 kilopascal, or 101,3 kilopascals at least. So we've got this atmospheric pressure that is a standard unit, and we can use this all the time. We recognize absolute zero is a standard temperature. It's equal to 0 Kelvin or minus 273 degrees Celsius. So chemistry is a whole lot of standards. And a standard just is a way of comparing things against each other. So for electrochemical cells, we need some standard conditions. And the standard conditions here are slightly different to the standard conditions for gases. We're going to say the standard conditions for the cells is a temperature of 25 degrees Celsius, which is the same as 298 Kelvin. We recognize that the concentration needs to be a standard as well. And we're going to take the solutions in a galvanic cell to be 1 mole per decimeter cubed. That's sometimes indicated as 1 molar. Now, not all galvanic cells have just a solution with an electrode. Some of them are gas electrodes, and the standard hydrogen electrode is one of those. It's using hydrogen gas. Where you have a gas electrode, you have an inert electrode, usually a platinum electrode. In some cases, it can be a carbon electrode, but usually a platinum electrode. The pressure for that gas has to be standardized. So the pressure only for gas electrodes, the pressure is going to be 1 atmosphere, which is equivalent to 101,3 kilopascals. And we make sure that we've got that all very clear as we go and look at our standard conditions over here. There would be a standard condition of 25 degrees Celsius, and the other standard condition is each of these solutions must be 1 molar. Okay, there's no gases here. And if that standard condition were met, then we know that that voltmeter will always read the same. And in this case, it happens to be 1.10 volts. And that's always going to be the same if you've got copper and zinc. So we must be very clear about why it's important so that we can compare things equally. Right, now let's go and look at our famous standard hydrogen electrode. Now, this hydrogen electrode, as you can see, it has hydrogen coming in over here. Notice that I called it kilopascals because I divided by 100, but in fact it's 1.01325 pascals, same sort of thing. And it's hydrogen gas that's going in there. It runs down here. There's the platinum electrode, and it's going to get into the liquid. The liquid is either hydrochloric acid of 1 mole per decimeter cubed. I've also seen them being used for nitric acid. So as long as it's just one hydrogen being available, then that is the standard hydrogen electrode. Now, you would connect the standard hydrogen electrode to other cells to make a galvanic cell. And the interesting thing, the reason why we're doing this is we're wanting to use this standard hydrogen electrode as a reference cell. So we're going to use this one as a reference. We're going to test all the other cells against this one and compare the reading on the voltmeter. And so let's do that. And we'll use our examples that we've been doing earlier. Here's the example of comparing the zinc anode with the standard hydrogen electrode being the cathode. And what you'll notice is that zinc is able to donate its electrons, and the electrons move through the voltmeter to the cathode, and at the cathode there is a reaction where the acid is gaining electrons to produce more hydrogen gas, where over here the reaction is the zinc ions, zinc metal is going into solution to produce more zinc ions. So oxidation here, that's why it's an anode, and reduction happening over here. So what I want you to notice very clearly is that we've got a movement of electrons and we've got a reading on the voltmeter. When the chemists first did this, they said, let's pretend that the hydrogen electrode will always be the anode. And they'll connect it to the voltmeter, expecting electrons to come from the hydrogen electrode. So when we get a negative reading, it's telling us the opposite half cell is giving us the electrons. So in this case, we're going to say the zinc half cell is the better reducing agent. Where this one, we're finding here, this solution is the oxidizing agent. So that's the reason why we're getting a negative reading there. Now, let's take a little bit of time to put that fancy diagram into cell notation. So we've already said that the zinc electrode is the reducing agent. So we're going to write zinc solid. Now, we're then going to put a line, vertical line, and we're going to say, what are the things that are being formed here? Well, it's zinc 2+ ions. They're in aqueous solution. And if it's a standard cell, you might be asked to show the conditions. So in that case, we're saying it's 1 molar. Then we're going to put in place the salt bridge, the link between the two. We're then going to say, what are the oxidizing, what's the oxidizing agent? And the oxidizing agent here is in fact the hydrogen ions. They're in solution, and they're also a concentration of 1 molar. Then we come to the electrode. Now, the electrode isn't really the thing that we're looking at here, because the electrode isn't the physical electrode. It's actually the species that's related to the ions in solution. So that must be the hydrogen gas. And so we're going to be very clear about that. Hydrogen gas, okay, and we'd recognize that's at a particular pressure, 101,3 kilopascals. And the final thing that we're going to do is put in the platinum electrode, which is the solid. So if you follow that pattern, you'll be able to get the cell notation. Very important, and I almost forgot it, we must say at 25 degrees Celsius. Now, the question should ask you to say at standard conditions, or the cell notation of a standard cell. If they do that, then you must put in the details like I have. If they don't, you don't have to. But please always put in your phase indicators. So always put in that it's aqueous or solid or gas, put those in. Right, let's move on. And what I want to move on to here is to show you that when we connect these together, we find that we've got a reading on the voltmeter of minus 0.76. Now, that reading of minus 0.76 is what we call the E naught of the cell. And so when we've compared hydrogen, we said it was the reference, we're going to make the hydrogen half cell 0. And everything is going to be compared to that. And that's why we're calling it the E naught of the cell. It's the reading on the voltmeter. Now, bear this in mind. We're going to do lots and lots of these readings. And in fact, let's move on and we'll look at the next one, which is the copper cell. There's the copper strip. And now what you recognize is we've got a positive reading on the voltmeter, and the standard hydrogen electrode is now the anode. The electrons are coming from that reaction. So this electrode, we're going to get oxidation taking place, whereas at this one, we've got reduction taking place. And you can see the movement of the copper ions onto the electrode, the electrons moving in this direction, and the reading is a positive reading. So that's slightly different from what we had before. Let's make sure that we can write the cell notation for this. Here, we're going to start with the anode. And you'll see we always start with the anode. We're going to start with the anode here as the platinum electrode. The reducing agent, in this case, is going to be the hydrogen, and it is the gas. I'm not going to put in the pressure, because let's just put it in 103 kilopascals. Then we go to the oxidizing species, which is the hydrogen ions in solution. That's 1 molar. We've got the salt bridge. The oxidizing species is the oxidizing agent is copper ions, 1 molar. And the final thing there is the copper solid electrode. If we look at the E naught of the cell, that's the reading on the voltmeter when we're comparing the copper half cell to the standard hydrogen electrode. And in this case, you'll see it's a positive value. And the reason for that being a positive value is this is the anode. And so the reaction, starting from there, the electrons are going in the voltmeter's been connected properly. The electrons are going in the right direction. That's the reading that we're getting for this cell. Now, what happens if we put not the copper together, but we put the zinc and copper together? What's going to happen here? So no longer have we got the standard electron, but what happens if we put the two together? Well, now we've got a formula here, which says take the cathode, and the cathode value will always be the one that is the positive value, or the more positive value. Remember, this one is more positive, the copper is more positive, so we're going to say that value of 0.34 minus the anode value, 0.6, and if you do that on a calculator, you'll get 1.10 volts. That's exactly what we're wanting. So guys, we can use these standard electrode potentials, E naught values, on our table to calculate the predicted voltmeter value. So that's quite an important skill. But you know what? I think that we just need to make sure that we recognize this standard potentials can be used in a number of different ways. And so please make sure that you recognize these, learn to work with them, understand the role of the standard hydrogen electrode, and make sure that you can do the calculations of the E naught of the cell using the data given. Hello everyone, welcome back. Let's get straight into it. What we're going to do now that we've laid a foundation, we have some idea about this table of standard reduction potentials. Let's see how we can use it, because it is actually a very useful table for us. Do you know what? In every exam, you're going to have access to this table, or to a similar one to the one that I'm using. But it's important that you don't just think, oh, well, all the information's on the table. Make sure you know how to use it and how to interpret by looking at the table. So let's dive in and let's particularly focus on what we're doing here. So I'm going to make sure that we're all sorted. The table of standard reduction potentials is very important because it helps us identify strong reducing agents and strong oxidizing agents. We'll also be able to use it to write net equations for a galvanic cell and to calculate the E naught of the cell. The E naught is equivalent to the EMF. So you might have heard that phrase used in terms of some physics work that you might have done. The E naught is essentially the EMF of the cell. So we need to be clear about this is the maximum electrical potential that can be delivered. And it's because of the difference in the nature of the half cells that we're using. So let's get in and have a look at the table and do some revision on the table so we are clear about it. So you will notice that on the table, everything is written as a reduction reaction. So reading from left to right, as we go there, magnesium plus 2 electrons gives you the magnesium metal. But notice, as I indicated previously, that it is a reversible reaction. And that means that when we read from left to right, we're reading reduction, and they're all written as reduction, but reading from right to left, we're reading the oxidation. And we know that if we're reading from right to left as an oxidation reaction, in other words, when we go from that side to that side, starting at zinc, ending up with zinc ions, that's an oxidation reaction. What we mean then is that all of these things that are on the right-hand side are reducing agents. And in fact, the table also over here says that when you're going up, you're increasing in their ability to be reducing agents. So which is the strongest reducing agent? Well, if the ability of reducing ability increases as we go up on the right-hand side, well, those that are higher at the top on the right are better reducing agents. So be clear about that. Sometimes the table might be switched around. There are 2 tables on some data sheets. Just make sure that you're using the one that you're familiar with, and recognize that lithium is given in this context, is the strongest reducing agent. The other way that you can do it, and you can learn it very clearly, is, as I pointed out earlier, when we looked at the comparison of zinc and the hydrogen electrode, the one that is the most negative, that negative value tells it that it's the reducing agent. It was trying to donate electrons to the hydrogen electrode, to the reference cell. So it is the source of electrons, not the hydrogen cell. So if we look at lithium, it's got the highest E naught value for that cell because it's most active in getting rid of its electrons and wanting to palm them off on the hydrogen electrode. These values all come from when you've taken the cell and connected it to the hydrogen electrode, the reference cell. And the reading that we get here is the reading on the voltmeter when it's connected in that way. So we can now, as I showed just now, compare different cells by connecting them together. It doesn't just have to be the cell and the hydrogen electrode, but it can be any two half cells made up of different substances. Before we get there and we start to take a look at that, let's have a look at the other end of the table. Now, the table is quite long, and I've even deleted some of the values. I just wanted to note over here, the hydrogen electrode, the reference cell, is at 0 value. Now, that value we've chosen as 0, and we've chosen it because at standard conditions, when you measure against that 0, you will get that reading on the voltmeter. Now, if we go to the next table, it's the other end of the table. And the clear thing here is on the left-hand side, you'll see fluorine. So fluorine is the most reactive nonmetal halogen, and it's also the strongest oxidizing agent. Please take note that when we talk about an oxidizing agent, we're talking about the thing that we see on the left-hand side of the table. And so it's the thing that is going to take electrons. It's going to undergo reduction. So the oxidizing agent takes the electron, and it makes something else out of it. In this case, fluorine would gain electrons, and it would make fluoride ions. And again, I've indicated the hydrogen electrode over there is the reference electrode. And notice that all these values are positive values because they're positive with respect to the hydrogen. They are better oxidizing agents than the hydrogen. In other words, when we connect these cells together, the hydrogen electrode, the standard hydrogen electrode, is the anode here, and these ones are all the cathodes. So that's why they're positive. This one is the best reducing agent of this lot in comparing these together. So we always recognize that the more negative something is, the better reducing agent it is. So even if we were to take, for example, something like iron 2 here and compare it to silver, we'd recognize this is plus 0.77, where silver is plus 0.80. The one that is more negative or closer to 0 is going to be the iron 2 plus. So if we had half cells of iron 3 plus, iron 2 plus, and silver, we'd recognize the iron 2 plus is going to be the reducing agent. That half cell is going to be the anode, where the silver half cell is going to be the cathode. This table, with these values on, as they've been written in this form, very important to be able to show the net reactions. So I'm going to do an example here of the type of reaction that we've done previously. So have a look at this. We recognize this is definitely the most negative, so it's the reducing agent. And if it's the reducing agent, we're going to find that we're going to take the thing that is undergoing oxidation. So zinc is the reducing agent. That means we must write that reaction down and flip it. So we're going to write down the reaction that's taking place at the at the anode, where the reducing agent is going to be zinc, going to zinc 2 plus, plus 2 electrons. That is an oxidation reaction, and this takes place at the anode. So the anode reaction is that one. We're then going to say, well, what happens at the other reaction? Well, the other reaction, the other half cell, is going to be the opposite one. It's going to be the reduction. It's more positive. So this substance here is the oxidizing agent. The oxidizing agent being the copper 2 plus. Copper 2 plus plus 2 electrons is going to give you copper as the solid, and that's the reduction reaction. Now, when we write the overall net reaction of a cell, we must make sure the electrons cancel out. And in this case, you can see quite clearly you've got 2 electrons that are gained there and 2 electrons that are lost, so there's no need to cancel them out. But what's important is to indicate the phase. Please make sure that you write the phases in, and when you write the net reaction, you're adding those together. So we say zinc in brackets with an S to say it's solid. Then we're going to write underneath what we've got, and that's copper 2 plus, aqueous, AQ, going to form, go back to the top line, zinc 2 plus, aqueous, and my AQ sometimes gets mixed up. You might not see it very clearly, but I hope you can. Copper as the solid. That's the net overall reaction for this half cell. Now, it's important that you practice them, and we'll give you an opportunity to look at some more. But for the moment, I think we should just take a quick break, and then we'll look at some more calculations as we use this table of standard reduction potentials in a little bit more detail. So we'll see you after the break. Welcome back. Let's get straight into it as we are looking at using the table of standard reduction potentials to do various calculations with galvanic cells. We've already seen how we can use the table to write net reactions, but the calculation of the E naught value is something that I think we need to spend a little bit more time at, and the way that we're going to do it is by answering a question. So let's go and have a look at our question. So it says to us, which combinations of half cells will give the biggest reading on the voltmeter? So the E naught of the magnesium zinc cell was 1,61 volts. I wonder if the iodine chlorine cell could give us a bigger E naught value. Well, I don't know. Let's go and see. So what you can see here is we've written down the reactions, not on the table, because sometimes that's exactly what they do in a question in an exam. And we have to look carefully at it, not expecting to learn all the values. In fact, they could have given us an equation that doesn't appear on their table, but gives us the E naught values for that reaction. And what you've got to be able to then do is identify which one is the reducing agent and which is the oxidizing agent. And how do we do that? Well, you should remember that the reducing agent is going to be closer to 0, or the more negative one of these two values, because both of these are positive. And so you might think, oh, nothing's going to happen. No, we're going to have to find the one that is closer to 0, that's the more negative. And that's the one that is the more negative. So you have to check this and make sure that you understand that the iodide ion is going to be the reducing agent. Now, it doesn't look like what we've done previously, because iodide ion is a non-metal. But it's the reducing agent, and it's therefore going to undergo oxidation. And so we would need to see that the iodide ion in this process is actually the anode. It's kind of different because when we were dealing with metals, the anode was where ions formed. Here we're dealing with non-metals, and the ions aren't going to form, but the metal, the element, is going to form. The non-metal, the element iodine, is going to form. So in this cell, we are going to need to rewrite the equation and turn it around. and see that it goes 2I minus, which is an aqueous solution, going to form I2 plus 2 electrons. And then what's going to happen in the chlorine gas? This, notice, is a gas electrode, so the chlorine is going to gain the electrons, and so chlorine is going to gain electrons to form the chloride ion, which is aqueous. Notice that that's a reduction reaction, so this is the cathode. So if we're going to do our E naught of the cell calculation, then we're going to say, remember, let's take E naught of the cathode minus E naught of the anode. But there's the other equation that's on the data sheet, which says instead of the cathode, what we're going to do is we're going to say, let's take the E naught of the oxidizing agent. Now, if you're not sure, you can check and write both down and make sure that you've got it, minus the E naught of the reducing agent. The reducing agent is on the right-hand side. So we're going to make sure that we get that right. We're going to write down the oxidizing agent, first of all, as 1.36, and it's positive, minus, and then in brackets, we're going to put the anode, or the reducing agent, and we're going to say 0.54. Now, we didn't have to have brackets because there was no negative there, but let's get the calculator out and just put those values in. 1.36 minus 0.54. And what we find is that the answer here is 0.82. So 0.82 volts. Again, notice that it's a positive value. So it is still a spontaneous reaction. It will generate some potential difference, but it's not as much as the magnesium zinc cell. Please don't let that give you the impression that metals are always better than non-metals. It's not always true. We can pick a whole range of non-metals, half cells, that will give you as big a potential as the metals. And in fact, choosing the biggest ones apart is going to give you the most overall. So to answer our question, which one is the biggest? This one was the E naught of the cell, was 0.8. Let me just check the answer there that we got, 0.82. So quite clearly, this one is the better, is going to deliver the better E naught value. So absolutely important to do these calculations and to be able to see how valuable this table is that you're going to take into the exam. It's like having extra help. So make sure you're comfortable with it, that you identify all the values from it. You know what? There's one other thing that I've learned over time, is sometimes people forget the polyatomic ions. And the polyatomic ions are on this half reaction sheet. So you can pick out what the charge of a sulfate is or a nitrate is. They're on there. Go and have a look for them. Let's just summarize what we've learned so far. And as we've been talking about the galvanic cell, remember it transforms chemical potential energy into electrical potential energy. The E naught of the cell is comparing a half cell to the standard hydrogen half cell under standard conditions. So it's telling you how much energy is being converted. That's what potential differences. It's the work done, energy per unit charge. And so it's a very good reading for that. Also note this, that oxidation always takes place at the anode. The reducing agent has the more negative E naught value, E naught of the cell value, compared to the hydrogen standard electrode. Of course, that tells us that the reduction takes place at the cathode, so the oxidizing agent has the more positive value. And when we combined an anode and a cathode, the half cells together, and we get a positive value, we know that reaction is spontaneous. So I hope you recognize that we've covered many aspects of the galvanic cell. And so just make sure that you've got all of those ideas clear in your mind. The galvanic cell is related to the redox reactions, that there are reactions at the anode is oxidation, and at the cathode is reduction. That there is a salt bridge, and the function of the salt bridge is important, that you can write cell notation, and you recognize this standard reduction potential all relates to the standard hydrogen electrode. Let's just summarize some details of the galvanic cell. Please remember the galvanic cell transforms chemical potential into electrical potential, and that is indicated by the E naught of the cell. Also, that oxidation takes place at the anode, very important to remember that, and that because of that, the anode is going to be the one that has the most negative E naught. Similarly, reduction takes place at the cathode, and this is going to be the more positive E naught value. Guys, I hope you've enjoyed being with me. I have really enjoyed this lesson, and I hope you excel at galvanic cells. We'll see you again soon.